Okay. 4 jars. I set them out in the rain when we had a lot of rain last week, so I get good data. And after it had rained, I weighed how much water was in each jar. Okay, they presumably would be getting water at the same rate per unit of area. Now I traced the lids of the jars. That's the outer circle. And of course, because of the thickness of the chalk and the thickness of the jar, that circle is bigger than the inner diameter of the jar. Then I just estimated where the inner diameter ought to be based on how thick the jars appeared to be and how far the chalk line was outside of the actual circle I was tracing because of the thickness of the chalk. And I got these inner circles. Okay. And I measured them about 1.5, 1.6, 2.5, 3 inches. And those actually are pretty close to what I think the inner diameters are. Now, the problem is it's impossible to accurately measure the inner diameter because the top of the jar, I don't know if the top of the jar is absolutely level or if it's beveled a little bit like this. So I don't really know where the locus of points is that separates the raindrops that go into the jar from the raindrops that go out of the jar, or the proportion of a raindrop that hits the edge that goes in versus goes out. And then you know, of course, you get into things like how does the surface tension relate to that, and maybe make that not quite totally accurate, but we're not going to talk about that. Anyhow, when I graph the weight versus the diameter, I get a graph that looks something like this. And I graph these without actually graphing the numbers. I just graphed these arrows down here, and then vertical lines through the arrows, and then the weights. Yeah. And this is not accurate. I just made up the weights, and the arrows aren't really quite right. This arrow, I think, is a little too short. And this arrow really ought to be about twice as long as this one. It really is. Here we have it, and here we have it, and here we have it. Anyhow, we could construct this graph without even measuring. Now, of course, if we want to get an accurate model, we measure as accurately as possible. Then we test. Now, we know that the area of a circle is proportional to the square of its radius or diameter. So what we should get here is part of a perfect parabola. Okay, we can test whether that's true or not. And we can test then the consistency of our data. So it's kind of a simple situation with a simple proportionality. And I'm using that right at the beginning of a pre-calculus course with, of course, more detail than I'm talking about right now. It's an interesting model. Well, I'll give it away to you. It turns out that the ratios of these diameters, or the ratio of the squared diameters, appears to be almost a perfect predictor of the ratios of the weights of the water, or the masses of the water. And actually it's weights, we measured weight, not mass. We didn't do an inertial mass. We didn't see how much force it takes to accelerate the water. We put it on a balance and measured the weight, even though the thing gives us grams, which is not a measure of weight. Okay. Anyhow, take that for what it's worth. It's kind of interesting. And it's really kind of fun to do this kind of experiment. When I knew in advance that it really pretty much almost had to be, I couldn't imagine anything that would throw this off by very much, till you get down to things like surface tension and your inability to accurately measure the diameter of the circle within which the raindrops fall into the container. Anyhow, it goes away, and we'll talk some about variation of parameters as soon as I get myself together here. enough to make this part of the board. Okay. Now, before we get to variation of parameters, I threatened to look at one of the homework problems. And I'll do that here. Okay, you have a differential equation. It's y. I'll go ahead and write four apostrophes here. Okay, there's the equation. And you correctly saw that this equation could be written then as, well, that the homogeneous equation. Okay, well, let's just say the left-hand side is annihilated by this. Very straightforward. We understand why it's annihilated. And of course, then this can be written as d squared multiplied by d squared minus 2d plus 1, which is d squared times d minus 1 quantity squared. Now let me get back to my screen here. Okay. Just making sure everything appears okay. And let me make sure that I'm actually using the decent camera. It looks like I am. Yep. Okay. And then the right-hand side is annihilated by what? Well, just plain old d annihilates the 1, and d minus 1 annihilates e to the x. So that the left-hand side is annihilated by the product of those two annihilators. And we established last time why that's a product and not a sum of the two. And hopefully you understand that. And if you don't, give it just a little more thought, maybe review what we did or read what the text tells you. It does a good job. Okay. Now, that means the annihilator of the entire equation is going to be the product of this and this. So this mess annihilates the entire equation. And of course, we can write that as d cubed times the quantity d minus 1 cubed. So this annihilates the entire equation. So you know, first place, what does d cubed annihilate? Okay. Well, it annihilates any quadratic. Okay, it annihilates ax squared plus bx plus c. Then, see, did they give you? No, they didn't. Okay. What does d minus 1 squared annihilate? Well, it annihilates I used A, B, and C here. I'm going to use, I'll use C1, C2, and C3. C1, x squared e to the x plus C2x e to the x plus C3 e to the x. Now, probably not a good idea for me to do this because of the way you formatted your answer. So I'm going to make this a D1 and a D2 and a D3. Doesn't matter really what we call these constants. It's going to turn out then that you need all these terms in your solution. And you gave your solution, you gave a C1 e to the x plus C2 plus 1/2 x squared. Well, all those terms match terms that we have up here. Okay, we have a multiple of e to the x right here. So your D3 would be a C1. We have a constant term here, C. So this C would be your C2. And you have a 1/2 x squared, which is just fine. That would correspond to this term. Okay. But you're missing some other terms. You're missing a term here, a term here, and a term here. Okay, so you would have then plus a bx plus an ax squared. And then let's say you're missing these two terms. So you'd have plus this and this. Now, these two terms correspond to this annihilator. Well, correspond to this part of the annihilator that annihilates the left-hand side. That would be part of the solution of your homogeneous equation. Where am I with my constants here? Okay, well, then you're going to have a d1 x squared e to the x. And we could call that, okay. Since this corresponds to the annihilator, the homogeneous part, we could put a C3 on this plus a C4 x e to the x. So if we had those four terms, then we could be assured that we annihilate the left-hand side. But of course, if you do the characteristic equation, you find that the solutions of the homogeneous equation include e to the x, which is why we get an x e to the x and an x squared e to the x. You get that out of reduction of order. Make sure you understand how that works and why that works. But then we also get these three terms. Now you have the 1/2 x squared, And why do you have to have a 1/2 x squared? Because when you take these derivatives, you got to get 1 here, okay? So you got to match up these coefficients with what you actually get here. So you got that one. You want to get the other two. You're going to find that this one is 0. And I've got ax squared there. And that should not be the c. That's that's redundant with the 1/2 x squared. Shouldn't have written that down because this c ended up here. Well, anyhow, work through the details and you end up with 6 terms and not 3. And it all comes out of the same process. Okay, well, let's see. There's another thing. And I think the same thing happened on number 11, but your constants weren't quite right. You can check out the constants. You got the right term. You got an e to the negative 10x and an e to the 10x, but then you got a negative 1/8. And that's going to, there it is. Okay. It's an initial value problem. The initial values allow you to determine the coefficients that correspond to the non-homogeneous part. I looked for those on the previous. And I didn't find any. But on this one, there are initial conditions that give you specific values. Okay. So it's the same thing, same process. So you might want to work through those and then email me or ask next time if you have additional questions. Okay, well, we're going to move on to variation parameters. And just to keep myself honest, actually, you did the variation parameters. And that worked out pretty well. I didn't see that when I looked just a minute ago. I don't know why it didn't show. Maybe you did the entire assignment while I was talking just to keep yourself entertained. I don't put it past you to be that quick, but most people couldn't do that. Okay. So that wasn't it. Just somehow WebAssign didn't give me the information it should have. Now, why did it do this? Because I clicked in the wrong place, that's why. Okay, well.
Although if anyone asks, we can just tell them that I did it that quickly.
Well, yeah, you're welcome to claim it. There's proof, I corroborate it, and you're officially now a genius, and I knew that all along anyway. So that's fine. Okay. Okay, now you probably have this example in your text, and I apologize for not looking. So I'll just throw an extra constant in. So if you have the equation, I'm going to give myself plenty of board space here. If you have the equation, very simple equation, kind of a standard equation to introduce this method. Okay. Variation of parameters, whether you use differential operators and annihilators or not. I mean, you could just ask yourself, what are you going to use to annihilate the secant? Okay. Well, derivative of secant, you got tangents and secants and that, and then you got product rules, and it just, you take higher and higher derivatives of the secant, it gets worse and worse, and you never get 0. So you can't annihilate secant of x. If you want to prove that to yourself. Just start taking derivatives of the secant. Every derivative pretty much doubles the number of terms that you have, okay? And also, equivalently, you can't come up with a trial solution for undetermined coefficients. That's written really bad. I apologize for that badly. So you can't do this, you can't do this. It's kind of an if or only if thing. If you can do this, you can do this. If you can do this, you can do this. But the bottom line is, nothing that we know works. Nothing we know is going to help you in any way to solve this non-homogeneous equation. Now, the homogeneous equation is easy. Your solution set is cosine of x, sine of x, which you can easily verify. Okay, and that's a curly brace there. Parenthesis. Okay, there's your solution set. Now, how do you solve the non-homogeneous equation? I've just gotten myself in trouble. I think this is going to work. I should have worked this out in advance. So if I got myself in trouble, that's all right. We'll figure it out. Okay, to solve the non-homogeneous equation, assume a solution y equals u of x cosine of x. Well then, y prime equals suppressing the x and the u of x to get u prime cosine of x minus u sine of x, and y double prime is u double prime cosine of x. Write that a little more clearly. U double prime of x cosine of x minus u prime sine of x, this term. And then here we have minus u prime sine of x plus u sine of x. In this case, our differential equation becomes y double prime. Okay, I'm trying to collect these terms. You're going to have a u double prime term here. You're going to have u double prime. I'm going to have to move this over a little bit so I can use as much board as possible. Okay. Equation becomes first of all, you're going to have a u double prime cosine of x. And that's your u double prime term. It's the only u double prime term. And then you're going to have plus u prime. Now you got a bunch of u primes here. You got a u prime times -2 u prime sine of x and a u prime cosine of x. Be careful. And it's not -2 u prime because we've already got the u prime up here. It's -2 sine of x plus cosine of x. And then, try to be careful again, we have a u term here, here, and of course, for y. And I take back what I said there. We don't have a y prime, so we don't have the terms from the y prime. So let me correct this. So we have our u double prime cosine x minus a u prime, 2u prime sine of x. And then it's going to be plus u times the sine of x here and the cosine of x there, and they're both positive. And that has to be equal to the secant of x. Well, now, we have still an equation in u and its derivatives, but it's still a second order equation. We want to reduce the order. So we do a little bit of magic, and we make one of these terms go away. And I'm going to stop for a second because I need to check out a reference so I don't take the wrong turn on this.